Hello everyone, this is Mrs. Tempest, and we are going to elaborate a little bit more on valence electrons today and learn how to draw a dot diagram. So our learning objectives are determining the number of valence electrons in an atom or an ion and drawing dot diagrams for atoms and ions. Alright, so the first thing that we have to remember from our last video on orbital diagrams and electron configurations is the valence electrons. These are going to be the outermost electrons in an atom. They're going to be located in the last ring on a Bohr model, so that's going to be the one that's furthest from the nucleus. These are going to be responsible for the properties of elements, specifically those chemical properties. So you should have learned how some metals are more reactive than others, and we're going to kind of discuss that as we go along in our course. These are going to determine how atoms react with other atoms, and they're also going to determine the type of ion that will form, so whether it forms a cation or an anion. These valence electrons, recall, are going to be found in the S and the P sublevels. And remember that the S block and the P block are going to be those representative elements. And what we're going to do is look for those valence electrons. They're going to be in our S orbitals and then our P orbitals. So they're going to be somewhere in here for all of your different elements. And these are going to be located in those highest energy levels for the atoms. So if we're given an electron configuration like we are here, we're going to look for the highest energy level. So in this case, the highest would be 4. And we're going to just look at those S and P sublevels. And what you would notice is that we're going to have 2 plus 3 valence electrons. So for this element, it would have 5 valence electrons. And then also keep in mind that we can take a shortcut and kind of look at our periodic table the way that it's laid out. And basically all of your group 1 elements will have 1 valence electron, all your group 2 will have 2. These intertransition metals will also have 2. They act a little bit differently than our representative atoms. Group 13 will have 3, 14 will have 4, 15 will have 5, 16 will have 6, 17 will have 7, and 18. Most of them will have 8 valence electrons, but remember that our helium will only have 2. So the reason that these different elements and atoms are going to form ions or react with other atoms is due to something called this octet rule. So with the octet rule, you can think of what oct means in like octopus or octagon. It's basically saying that most atoms are going to react or change to obtain 8 electrons, and that will give them a full outer shell. So by having a full outer shell, it makes your atoms stable, and they're going to be more like the noble gases. So they strive to be like the noble gases because the noble gases are super stable. Now your atoms are basically going to lose or gain electrons or share electrons with other atoms to make this happen. There is also something called the duet rule, which is kind of an exception to your octet rule. So recall that hydrogen and helium are in period 1, which means that they're in energy level 1. And that energy level can only fit 2 electrons in that outer shell, because it can only hold 2 electrons. It only has that 1s orbital and sublevel. So knowing the valence electrons, we can then draw electron dot models, also known as Lewis dot diagrams. So you might hear those interchangeably called different things, but basically we're going to express or show the number of valence electrons in the atom by using dots. So how we draw neutral atoms with these Lewis dot diagrams is first by writing the element symbol, determining the number of valence electrons, and then putting electrons around the symbol, 1 on each of 4 sides before doubling. So for hydrogen, if you look at your periodic table, remember that hydrogen is going to be in group 1, so it's only going to have 1 valence electron. So my hydrogen, I'd write the symbol like I have here in my examples, and then I would just put the 1 valence electron. With carbon, so carbon is in group 14, which means that it's going to have 4 valence electrons. Now remember that with electrons, we're going to put it around the symbol before we start doubling. So carbon, I would do 1, 2, 3, 4 to show my dot diagram of where the electrons are, or how many electrons it has. With fluorine, fluorine's in group 17. It's going to have 7 valence electrons. So once again, I'm going to put 1 on each side before I double up. So I'm going to have 1, 2, 3, 4, 5, 6, 7. So if we looked at the representative elements in a periodic table, you'll notice that the groups are going to have the same amount of valence electrons per elements in that group. So the dot diagrams are going to look really similar. The only difference is going to be the element symbol that's in the middle. So here we can see that all of the ones in group 1 are just going to have that 1 valence electron. And over here, most of them are going to have your 8 valence electrons, but that exception being helium can only have 2 valence electrons because it's on that first energy level that can only hold 2 electrons. Okay, so with forming ions, recall that atoms are going to react or change in order to become more stable and have their outermost energy level completely full. So the goal is to have that outer energy level full. And that means that these atoms are either going to get 8 electrons in their outer energy level, or they're going to have 0 in their outer energy level, which makes the second most outer energy level the full energy level. It makes them happy. So if we take an example of sodium. So sodium is going, if I draw a Bohr model, sodium is in the 3rd energy level, and it's going to have 11 electrons. So I'm going to put my 2 on my first, 8 more on the second, and then 1 more on the third. So that's my 11 electrons. All right, so with sodium, right now, it is really unstable, which makes sodium super reactive. So if you remember that those alkali metals, the ones all the way to the left, are going to be really reactive. And the reason is that they have this electron, this extra electron on the 3rd energy level, and they just want to get rid of it. So basically with sodium, it's in group 1A, or the alkali metals. And what it's going to do is lose that 1 outer electron. And when it does that, remember, when I lose electrons, I become positively charged. So it would create that +1 ion. With group 2, or the alkaline earth metals, those are going to lose 2 electrons to form a +2 cation. Group 13, or 3A for our representatives, are going to lose 3 to form a +3 cation. Group 4 is pretty interesting because it can either lose 4 to form a +4 cation, or it can gain 4 to form a -4 anion. And it really is going to depend upon what other elements are around to react with it. So that would be group 14 on your periodic table as well. Group 15, or 5A for the representatives, are going to gain 3 to form a -3 anion. So if we're looking at this, one example would be for nitrogen. So nitrogen has a atomic number of 7. So if we think of nitrogen and we drew a Bohr model, so we'll have 2 here, and then 1, 2, 3, 4, 5. So with something like nitrogen, its outer energy level, it's going to be easier for nitrogen to gain 3 electrons from other elements than it is to lose all 5 of its outer shell electrons. So basically with nitrogen, it would gain 3 electrons, and that would make it a -3 charge because it has 3 more extra negative charges. Group 16, or group 6A, is going to gain 2 electrons to form a -2 anion, and group 17 or 7A, is going to gain 1 to form a -1 anion. Now remember, we also have group 18 or 8A, and those are going to be our noble gases. So according to the octet rule, noble gases, most of them are already going to have 8 electrons or 8 valence electrons. So those are already going to be stable and they're not going to create ions. Now what I like to think is that these atoms like to be happy, and they're happy when they're stable, and basically they're going to do the easiest thing they can to create an ion or to be stable and happy. So with groups 1 through 3, they're going to lose electrons because it's going to be easier for them. For groups 5 through 7, they're going to gain electrons because that is going to be the easiest way or the lowest energy way to become happy or to become stable. Okay, so when we're drawing the dot diagrams for ions, it's going to be very similar to the way that we do it for neutral atoms, but we need to either show more or less electrons depending on if it's going to be an anion or a cation. We're going to start off the same way by writing the element symbol, and then we're going to determine the number of valence electrons for the ion. So this is where you're either going to have more or less electrons. Then we're going to put the electrons around the symbol, one on each of the 4 sides, just like we did before. And then we're going to draw brackets around the dot diagram, similar to what we did with our Bohr models. And we're going to place the charge in the top right corner of the model. So let's do a couple examples together. So the first one would be sodium. Now if you look at sodium as an atom, you'll notice that it has 1 valence electron. So if I was drawing this as an atom, I'd put that 1 valence electron. But since I'm drawing it as an ion, all right, I know that it's in group 1 or 1A, and it's going to lose that valence electron. And when it loses that valence electron, it's not going to have any, or it's going to have 0 electrons in that outermost shell. So I'm going to put that brackets around my sodium because it's not going to have any dots to represent electrons. And then I'm going to put that charge in the upper right corner. So keep in mind when I say that it's not going to have any electrons in the outermost energy level, it basically is going to shrink down and act as if that second energy level is its valence electron shell. So sodium, if you remember the Bohr model from the last slide, it's still going to have an outermost shell that is full because it's basically going from the 3rd energy level to the 2nd energy level. Aluminum, remember, is going to have 3 valence electrons as an atom, but since, again, aluminum is going to lose those 3 electrons, technically it's going to have 0 in its outer shell, or it's going to shrink its outer shell. So we're going to put the brackets around it and give it its +3 charge. And then finally for fluorine, so fluorine has 7 valence electrons as an atom. All right, and since fluorine has 7, it will be easier for fluorine to gain an electron to have that full outer shell. But when it gains this electron here, that's actually going to give it a -1 charge because now it has 1 extra electron than it did as an atom. So here's another chart that kind of explains these different ions and electron dot diagrams that will form when you're either gaining or losing electrons. So if you guys have any questions, please make sure that you are asking your teachers.